Hello, and welcome back to this course on causality for psychologists and social scientists. This is actually now part two on directed acyclic graphs and theory specification. And so in order to introduce you to this topic, I wanted to remotivate causality from a slightly different perspective, maybe from more of a statistical perspective. And then I'll introduce directed acyclic graphs, give some examples of directed acyclic graphs in psychology. These are just going to be simple toy examples to help us familiarize ourselves with the formalism and the mechanics of directed acyclic graphs. I'll talk about some challenges, and then eventually we'll talk about some of the rules, the key rules of directed acyclic graphs, and specifically their conditional independencies, that is, the statistical independencies that are assumed to be present in the data once we specify our graph. I'm going to assume for most of this that we're dealing with linear relationships between variables, although almost all of what I talk about will generalize to nonlinear examples, non-parametric examples. In fact, that's one of the strengths of this framework. So in order to remotivate this from a slightly different angle, recall that I argued that, not just me, but other researchers as well, that most theories in psychology are underspecified and untestable in psychology. They're primarily proto-theories rather than really what we'd think about as theories. And indeed, sometimes when I talk to other colleagues from different disciplines, they kind of raise their eyebrows at me when I say, we're dealing with this theory. We have slightly different ways to use the word theory, but I think actually we can make our usage of the term similar if we can start to formalize our theories. So we need something formal, some kind of process to go through to take our proto-theory from something that is more descriptive, potentially still very rich and full of information, to something that's unambiguous and well formalized. And this is going to help us, if we do so, to think more carefully about the specifics of our theory, because now, rather than just describing lots of different sort of rich nuances or subtleties or even the broad strokes of the theory, we actually have to sort of tie it down into something that's unambiguous and mathematical. And this will also help us understand if what we care about in terms of our specific research questions relating to something about that theory is actually going to be testable in practice. And that also is going to help us design the data collection methodology. So the perspective that I'm going to take is as follows. This is a simplification of maybe the way things are, but nonetheless, this is going to work for our purposes. I'm going to assume that there exists a very complicated real-world causal process. And arguably, it's not just about this planet, it's also about the universe, all the molecules within it. And this gives rise to a set of states, i.e. at any particular time, the universe is in a particular state. Now, we can partially observe these states. We can't capture a snapshot that captures everything about a particular point in time, but we can go in with a sort of noisy camera and try and take some kind of snapshot of that state. So when we give someone a questionnaire, when we design a sort of a scale to be able to measure something that's maybe latent, for instance, we're trying to extract some kind of representation of the state of the world. And some of those states are very difficult to measure. But we're going to assume that we can partially observe these states. And once we've got that, that's essentially our data set. Now, on the other hand, we've also got our model or our theory that describes the data generating process that gives rise to those states in the world. And this theory is going to be a dramatic abstraction from the complexity of the real world process, which will include, arguably arbitrary levels of complexity going down to modeling individual molecules. But actually, we're going to sort of lump a lot of this together, and we're going to have an overall theory that kind of captures the broad strokes and the most important fundamentals of that process. But this is kind of our creation, and we want to iteratively improve it. But nonetheless, it's our representation of what goes on in the world. And so it's a really hard task to go from this real world process to a theory that works well. And then after we've got that theory, we want to have an analysis with a particular research question or an estimand. In statistics in general, we often have, say, a beta coefficient in a linear model that corresponds with a particular quantity that's also described in the hypothesis. And then this can also be related to the real world process and our theory. I'm going to argue that, this theory is very vague at the moment. It's not a mathematical object like this is here a graph. It's more a long verbose description of a phenomenon. And then because of that, and by consequence of that, our analysis is also kind of vague and not clearly tied to a theory. And again, by consequence of that, the estimate, the thing that we want to estimate, is also kind of loosely tied to our theory. And it's all kind of a bit circular and a bit difficult to understand what's going on. So what we want to do is really formalize this, a bit like how we've got here, where we admit that there's some complex process. We're going to specify that process unambiguously as a mathematical object. And then our going from the theory to the analysis is also going to be just a technical process of making sure our analysis is consistent with that theory and the thing that we want to estimate. So as I said, I've used the word consistent. I want all these components to be consistent with each other. They can't be the same. They can't map one-to-one to each other because, again, for a start, going from this real-world process to this theory, there's a huge amount of simplification that goes on there. But we want it to be consistent to the extent that, this theory is useful to us when we generate new predictions or reason about different outcomes under different situations. We want everything to be consistent so that things are meaningfully useful to us. And to motivate that, let's say we go out and collect some data without a theory, and we collect these data here. And this is actually taken from the primer on causal inference by Pearl, Glimore, and Jewell. And so we collect some data on whether or not people recover from a particular ailment, particular disease, following the fact that they've taken or not taken a drug. So if we just collect data for men, we might find that 93% of men recovered who took the drug. And in contrast, only 87% of men recovered who didn't take the drug. So just based on these data alone, notwithstanding the measurement error, there's some confidence intervals around these estimates. We might argue that, okay, well, on balance, this drug is good for men because more people recovered from the disease when they took the drug than they did when they didn't take the drug. So it seems to aid in recovery. Now, if we do the same thing for the data that we collect for women, we find a similar phenomenon. So we see that 73% of women who took the drug recovered, and only 69% of women recovered who didn't take the drug. So we might also say this drug is good for women. But when we combine these data and we just simply sum them up and again take the sort of percentage, the proportion that did recover or did not recover, we actually find a reversal of these numbers. And there's no trickery going on here. It really is just summing these numbers together, which could easily happen in reality. These aren't sort of miraculously or chosen, these numbers aren't specifically chosen to give us this effect, but we might find that overall when we combine these data, we find that actually they're bad for people because only 78% of people who took the drug recover, whereas 83% of people who didn't take the drug recovered. So here we might say, well, don't take the drug if it's bad for people, but it seems to be good for women and good for men. So this is actually what's known as Simpson's paradox. And it leads us to an important question, which is, should we prescribe the drug or not? So if we don't have a theory, it's actually very difficult to know whether we should prescribe a drug or not. Should we prioritize these subgroup results, or should we prioritize the overall results? And here it's a bit of an unknown at this stage. And this is a sort of a visualization of this. This is, I think, taken from a Stack Overflow post, I'm not sure. But here, this is a different number of groups. So rather than just men and women, there are 3 subgroups. And you can see that whilst overall there's this positive trend here, for each subgroup, there's a negative trend when we condition on those 3 subgroups. And so again, the question is, well, should we be conditioning on the subgroups, or should we be looking at the overall slope? And actually, Simpson's paradox has been described as a tale of statistical agony, the argument being that actually this paradox isn't really a paradox at all. It's kind of an obvious problem with an obvious solution, if you consider the causal theory behind the process. And so what we're going to do is to demonstrate the utility of causality here is to try and add some domain knowledge. So maybe you're an expert in this area and you happen to know a couple of things about the drug and how it works. And you might know, for instance, that estrogen has a negative effect on recovery. So that's a fact that you know. And we might also know that women take the drug more often than men do. And this is a fact that you can actually see in the data we saw, if we go back, that there are more women that take the drug than men. And this might be, for instance, due to the fact that there's more efficient targeted advertising for women than there is for men. Maybe women see the advert and feel more drawn to it than men do. Whatever it is, we can come up with a possible explanation for that. But we're pretending that we know this already. And so as a consequence of these two facts that we're acknowledging or assuming to be true for the sake of this example, we know that if we select a drug user at random, they're more likely to be a woman because women are more likely to take the drug than men, again, potentially as a result of this advertising. But they're also less likely to recover because on average, we know that women have higher estrogen levels than men. So if women have high estrogen levels and they're more likely to take the drug, then we see that women are less likely to recover than men are. And as a result of this, we kind of need to compare subjects of the same gender, because otherwise we're going to be attributing the effect of the drug wrongly to the effect of estrogen, which isn't part of the process by which the drug works. So here, the consequence is that we need to condition on or compare subjects of the same gender. So when we condition on, we sort of zoom in on a subset of our data. And by doing, we sort of ensure that differences in recovery rates are not spuriously ascribable to estrogen instead of what we care about, which is the effect of the drug. So we can represent this situation graphically. If we have the variables gender, whether or not someone takes the drug and their recovery, we know that there's a causal mechanism due to the drug. That's actually what we're interested in, where taking the drug actually improves the chances of recovery. We know that there's a mechanism due to estrogen. So women say have high levels of estrogen. This affects their recovery. Men have a lower level of estrogen, which also affects recovery, but not to the same extent. But then there's also this causal mechanism resulting in the skew of whether or not a man tends to use the drug or a woman tends to use the drug. And so you can see here that this causal mechanism from drug to recovery, we're indicating that causal mechanism with this arrow. We can take that path. We can go straight from the drug to the recovery, and we're interested in this mechanism. But there isn't another causal mechanism that goes via gender. The drug doesn't change someone's gender. It also, at least based on this assumption, doesn't influence their levels of estrogen. So there is not an alternative causal path. So every other part of this variance in recovery is due to this gender variable, but that's not part of the causal information that we want that we care about. So really what we want to do is partial out the variance in recovery, which is non-causal. In this case, it comes from the gender. So we want to partial that out by conditioning on it. So we end up zooming in on men and women separately in order that we're not sort of aggregating the causal mechanisms that result as the statistical association and the variance in recovery that results as a product of both the causal mechanism due to the advertising and the estrogen levels. So with this structure, and as I'm going to talk about in much more detail later on, we can see that, well, gender is a non-causal kind of influence on both whether or not someone takes the drug and recovers. And so it's non-causal to the extent that it doesn't, that taking the drug doesn't influence gender along this path. So we can use this graph to understand whether we should condition on gender as an example. Now, to contrast that against something which is similar in terms of its appearance, but fundamentally different as to whether or not we're going to condition on it, consider maybe this alternative set of results. So consider the data that we had before. The numbers are exactly the same, but instead of men and women, we're now conditioning on people with high blood pressure and low blood pressure. So now we might have this mediation structure here where we have the drug has a direct effect on recovery, but it also has an indirect effect on recovery via blood pressure. Here we might say that the drug lowers blood pressure. And if you have a lower blood pressure, you're more likely to recover. But at the same time, maybe there's a toxic mechanism due to the drug itself. So there's some side effect that actually affects also whether or not we recover. Now, in this case, blood pressure is part of the causal mechanism. So the recovery varies as a product of both the drug, the direct use of the drug here, the toxic mechanism of the drug, and it also varies because of the blood pressure. So now we don't really want to partial out the variance in recovery that's due to the differences in blood pressure, because that is part of the causal mechanism that we care about. So to remove that variance is actually to discard part of the causal effect that we care about. So in this case, we wouldn't condition on blood pressure. If we had exactly the same table as before, we had high blood pressure, low blood pressure, and then overall, instead of men, women, and overall, in the first instance, we wanted to condition on gender because we didn't want the variance in recovery to be ascribable to the different levels of estrogen, for instance. And in this case, we don't want to condition on the high and low blood pressure because that's actually part of the variance that we're interested in incorporating into our assessment of the drug. So for instance, here, even though we can see that it works for people with low blood pressure, it works for people with high blood pressure, but it doesn't seem to work with people overall. Well, whereas before we would just be looking at the men and women separately, now we want to actually look at the combined results, and this is more meaningful. And this is because, as I said, lowering blood pressure is a mechanism which affects recovery. We don't really want to separate the data and discard that variance because it's part of the causal effect that we care about. And in this case, blood pressure is actually a mediator of the effect from drug to recovery. There's a causal process that incorporates blood pressure as part of the efficacy, the mechanisms by which the drug works or doesn't work. So it's exactly the same data numerically, but we come to completely different conclusions. And so we can actually know this based on the structure of the graph, and we'll talk about this, as I said, in more detail later on. But in essence, if we condition on gender here, it's a good thing because this is a non-causal sort of relationship. Drug does not cause gender, does not cause recovery, but here drug does influence blood pressure and that does influence recovery. So in the first instance, we want to condition on gender, and the second instance, we don't want to condition on blood pressure, even though our tables, our statistical results may look exactly the same in both cases. So in other words, presented with a data set, it's impossible to know without this causal knowledge which results you should care about. And what I'm arguing is really to motivate the use of directed acyclic graphs. And in fact, these are two examples of directed acyclic graphs. Using the mechanics and the framework of directed acyclic graphs will help us understand what to condition on. And to that extent, it helps us solve these paradoxes. I wanted to mention a little bit of imprecise mathematics here. I don't expect people to be familiar with all of this, but it is very useful. When we have a linear model, say y equals beta naught, the intercept term plus beta x, this is the coefficient on x times the variable x plus some noise, we're kind of arguing that this model is an efficient or an appropriate approximation to modeling the expectation of y given a particular value of x. And what I'm going to tend to use is this expectation notation because it's much more general than always writing out a linear model. And as we're going to move towards machine learning models, we're going to want to move away from an explicit specification of that model in parameterized form to a more general representation of that model. And here, what we're interested in is, say, the expectation. So just to make that a little bit more intuitive, imagine we have two variables, y and x. So x along the x-axis, y along the y-axis. Imagine we've got this function here that describes the mapping from x to y. And there's some of this extra noise that sort of is added after this sort of mapping from x to y. And really, this tells us that, for any particular value of x, say x is age, for instance, what relates age to this outcome, it's not a one-to-one mapping because after we've got this sort of function, we've also got a possible spread either side of that possible y value. So we're not looking at the exact value of y given x. This is not a deterministic relationship, but rather we have an expected value of y given x, and that's on this line. And either side of that, we could be higher or lower. So for any particular value of x, there are multiple possible values of y. In fact, there's a distribution over y. And that's why we're interested in the average or the expected value of y, which describes the sort of the path through the middle, the nice smooth line that goes through the middle of all of this noise. As we'll talk about when we come to machine learning, the goal is to try and not fit this noise, I estimate this expectation. And so I'm going to use this expectation quite frequently to help denote what we're interested in. We're also going to find that there's a nice correspondence between when we use linear models, say using ordinary least squares to derive the values for the beta coefficients in this model here. If we were to then generate predictions using this model and set x to 0 and x to 1 in both cases and generate some predictions for y, we'd actually get the difference between those two sets of predictions on average will actually be equal to our beta coefficient. So in other words, it's the same as the interpretation of a beta coefficient in general. We say that for one unit change in x, the outcome changes by beta x. And here in the same case, if we have this model and we generate numbers for y for two different values of x, and we calculate the difference between them, we actually still get this beta value. So it tells us how much the outcome changes for a 1 unit change in the input. And that's going to be very useful to us as well, because we can actually express this in terms of expected values. And the equivalent value here is the difference between the expected value of y given x equals 1 and the expected value of y given x equals 0. And so this is just a little sort of formalism that we're going to be using throughout. And I just wanted to sort of give you an intuition as to why it's useful to us. Now, this particular quantity here doesn't tell us that it's necessarily causal. It just tells us how the regression model behaves. It gives us an idea of how much the outcome, as predicted by that regression model, changes in response to a change in one of the predictors. But if we do use causality properly, this doesn't just correspond with how the linear regression model behaves, it also corresponds with the causal quantity. In other words, the difference between the expected value of y under two different settings of x is actually the equivalent to the average treatment effect, where we assume maybe that x is actually a treatment for people that do take the treatment t equals 1 and people that don't take the treatment t equals 0. And so I'm also going to be using this do calculus notation. Do calculus is Judea Pearl's invention and colleagues. I recommend his book on causality to get familiar with do calculus, but we're going to be using it in a very sort of top level way to specify in an idealized case what we're interested in. So the average treatment effect could be expressed as follows, as the difference between what happens when we go in and we do treatment equals 1 and when we go in and we do treatment equals 0, I do and don't. And to this extent, this is a sort of theoretical quantity here. And our task, and using the rules of DAGs, as I'll talk about, will be to be able to go from this theoretical quantity written out in terms of do operators, which kind of describes the idealized case when we can perform an experiment, when we can manipulate ourselves as experimenters whether or not someone gets treatment or not, and being able to estimate this from the data that we have to hand, which is probably not going to be experimental, which is going to be observational data. So just to make it clear, this expectation is kind of like a long run average. It's something that we're going to estimate. It's not going to be something that we have direct access to. We're looking at the difference between these two expectations in terms of the outcome and under two different conditions. One when we have treatment and one when we don't have treatment. And this do, as I said, signifies intervention. It's almost like an idealized experimental quantity. Here's all the information altogether. And to see what that might look like, if we do have a randomized control trial, for instance, and we are able to do treatment equals 1, do treatment equals 0, maybe we can assign these treatments and not treatments or treatment and control randomly, in which case we may have the outcomes listed in our data set under these two different conditions. So here, these columns correspond with whether or not someone recovers. These are kind of like the outcome results for the group of people in the treatment group and the group of people in the control group. And to this extent, when we look at the expectations, and in a binary case, that's the same as the probability of recovery, we can just count the numbers up. So under this group here, we count up how many people recovered out of how many people in that group, 7 out of 10. With no drug, we find that only 5 out of 10 recover. And then we can express that in just the same way that we did before. We can look at the difference between the expected value of y given that we do treatment equals 1 and the expected value of y given we do treatment equals 0. We can approximate that empirical average just by computing this expectation just by using the empirical average. So we count up the numbers in group 1, which is yi for those that did get the treatment, divide by the number of data points there are. We find it's 0.7. So the probability of recovery when you take the drug is 0.7, and contrast that in exactly the same way for the group that didn't take the drug. The probability of treatment or the expected value of y is 0.5, compute the difference, and the average treatment effect is therefore 0.2. So this is kind of just to show what happens if we did have access to experimental data. That's kind of what our do notation is trying to tell us. Now in practice, we're more likely to come up with a data set like this. We're also probably going to have a whole lot of covariates that make it difficult to establish causality from correlation. But imagine just for now that our data set is actually just a combined version of these things, and that we can go directly to correlations, directly from correlations to causations. We might have, for instance, a list of outcomes and a list of whether or not someone was in the treatment group. And then we can fit a linear model, say y equals some intercept term alpha plus tau, the treatment effect on the treatment variable here, 1 or 0 plus epsilon. And once again, we can generate outcomes and compare the outcomes under two different treatment scenarios. One when treatment equals 1, we could set all of these to 1 and generate some predictions, set all of them to 0, generate some predictions, and it gives us the same result, the average treatment effect. So now we're conditioning on T, which gives us the same sort of results as we would have if we had two separate groups and we were to just compare them. So actually, if you work through this and you just condition on T, you get exactly the same results. You end up with 0.7 minus 0.5 equals 0.2. Okay, so in that example, we saw that conditioning on T was the same as conditioning on the do calculus operator of T. But in practice, it's going to be a bit more difficult than that. And so we're going to see how to do that. But main message from here is just to get used to this expectation sort of notation and also the do calculus notation, which is just to describe in principle what we want access to, this causal quantity. And then we're going to describe how to go from the do calculus version of that estimate to the estimate that's just written in terms of conditional expectations. And in this case, where we have, say, a randomized control trial, when we've been able to do this sort of experimental assignment of treatment and control, we have a sort of graph like this. We have whether or not someone takes the drug T and the recovery Y. We may also have some extra variables like age, which I didn't have in that previous graph. And you see that there's no incoming arrows to drug. Nothing influences whether someone's going to take the drug or not, because we're randomly assigning it. So whether or not someone takes the drug is actually the product of a completely exogenous random process that we don't need to model in terms of its relationship to age or any other covariates. So here's that random assignment expression here, UT being some exogenous noise. You could model that, say, with a Bernoulli distribution, with a probability of 0.5 being in the treatment group or in the control group. And notice that I didn't include X in the conditioning statement here. It's actually worth including X, though, because it can improve your estimation of the effect of treatment on recovery. So already, actually, we've seen a few example graphs and some useful mathematical formalism, very loosely presented, just to get you familiar with the sort of tools that we're going to be using. So those graphs are actually directed acyclic graphs. We'll talk about them in more detail. They're very intuitive because they're very visual. And actually, most of you are probably using something similar already. You may even be sort of sketching your theories on a sort of napkin, and you imagine this sort of process of something affects something else. You may also be familiar with mediation models, which are actually a sort of type of causal model. If you've used structural equation models in psychology and social science, again, it's kind of a visual representation of a directed acyclic graph. And they help us convey a lot of crucial causal information, which can help us, for example, solve these statistical paradoxes like the Simpson's paradox. They enable us to unambiguously represent our assumptions about the causal process, and they have relatively weak assumptions built in, at least about the functional form relating variables. So for instance, in this graph here, treatment to outcome, we don't necessarily assume that the treatment has a linear effect on the outcome. It could be highly nonlinear. And we assume some very strong assumptions about causality, though. So even though there's weak assumptions about the functional form, we have to make assumptions about, these are actually causal processes. This is what the graph looks like. This is the data generating process. But that's part of the specification of the graph. And whilst there are many other approaches to dealing with causality, you might have heard of potential outcomes framework, for instance. I find directed acyclic graphs are a little bit more accessible, particularly for those who aren't necessarily highly statistically motivated, but really want to just start grappling with their theory in a visual way that's nonetheless got the advantages of some mathematical formalism. So I want to acknowledge, haven't we seen this all before? And I mentioned before, mediation models are a type of sort of causal model. Also, the structural equation modeling framework can be interpreted in a similar way to directed acyclic graphs. But actually, in structural equation modeling, the arrows are almost always linear functions, whereas DAGs permit any any function in theory. There's some limits there, but they're relative. They're not that important for us. And see, for instance, the well-known bifactor model of intelligence here. You can see that this is a sort of structural equation model with some latent variables, S1, S2, and S3. These are latent variables that are specific types of sort of intelligence. Then we have the general factor G here, and then we have our measurements Y. And so there are some different formalisms when you're using SEMs. For instance, the round variables are unobserved, the square variables are sort of measurements. But nonetheless, actually, many of these core concepts carry over to directed acyclic graphs as well, but they kind of tend to be forgotten about. So, all of the rules that we're going to be talking about throughout this course are kind of forgotten, which is a real shame. So a lot of the example graphs that we're talking about, I mentioned this earlier, they're going to be unrealistically simple. And my goal is not to just say, well, we were kind of doing a 3-variable mediation model and we're just going to call this a DAG, and before we called it a 3-variable mediation model. That's not the message that I want you to take away. I don't want us to end up again on the wrong side of parsimony. I don't want our models to be too simple. I obviously also don't want them to be too complex, but just because the examples that we're using are going to be sort of very simple doesn't mean that they're the sorts of models that I want yours to look like. Actually, your process may be very much more complicated, and I think there's a lot of value in overcomplicating it, at least at first, so that you don't risk missing something really important as part of your theory development process. As an introduction to direct acyclic graphs, I want to start off by describing the sort of structural primitives. That is to say, you can construct any directed acyclic graph with these three substructures. That is a chain, which is A causes B causes C, or the other way around. A fork, where B is causing A and B is also causing C. And then a collider, where A and C are jointly causing B. And for the moment, ignore these dashed lines. I'll talk about them soon. But for now, just note that we can sort of create any graph using these primitives. Note that we have to avoid any cycles in our graph. That's why the name is directed acyclic graph, i.e. there cannot be cycles that are present in this structure. And as I'm going to sort of hope to demonstrate, most of your sort of research questions will probably be able to be represented in terms of some kind of sort of canonical structure that resembles this, i.e. you have some fundamental treatment variable or something that you want to contrast. It may not actually be a drug or a therapy. It might be, say, a group assignment, for instance, and some outcome. And then as part of that process, you'll have some set of mediators, some set of confounders, which affect both the group assignment and the outcome, some precision or risk variables that affect the outcome or recovery, but don't affect the treatment, some independent variables that have got nothing to do with anything really, some instrumental variables that just affect the treatment, and so on. And we're going to sort of see that these sort of structures pop up a lot. And it's going to be helpful to be able to communicate your graph to others or specific parts of that graph to be able to say, these are mediators. And then it becomes immediately clear what you mean by a mediator in reference to, say, the core variables, core treatment and outcome variables of interest. And the main assumption here is that this isn't just a sort of probabilistic graph, but it's not just that, but it's also a causal graph, i.e. these arrows specifically encode your assumption that there is a causal mechanism that exists between, say, in this case, an instrumental variable and a treatment variable. And so they're very similar to structural equation models. In fact, it's just a more general form of structural equation models where we permit nonlinear functions. We don't make assumptions about the functional form. And underlying a graph is a sort of implied structural equation model or structural causal model, which is more general than the SCM. And we could say X here is actually some function fx of some random noise or random process ux. M here is some function fm of x, but also its own random noise um. And finally, y is some function fy of its parent variables m and x, but also its own random noise variable uy. So we have to acknowledge that this is not a deterministic process. So we can't just take the value of x and calculate one value of m, but actually there's also some random noise that leads to variation in m as well. So we admit that this is sort of a random process, and all these variables are random variables. And as I said about the functional form, if we were in sort of structural equation modeling land, we might say that y is therefore maybe equal to beta naught, the intercept, plus beta x plus beta mm plus uy, which is a linear function. But we're actually wanting to admit sort of more general functions, just fx in general. It could be anything. It could be the identity function. If ux is a Gaussian noise, we might just say that fx is the identity function, therefore x is just some Gaussian noise, for instance. And notice also that I've used these assignment operators, not the equal sign. One of the arguments as to why causality is taking so long to catch on is because we're sort of very familiar with the equality sign, which is sort of for which we can sort of rearrange stuff in an equation sort of how we like. But actually in causality, there's a very asymmetric relationship. If A causes B, it's not the other way around. So just rearranging the equation is sort of not permitted. So in this case, these assignment operators tell us that M is a function of what came before it. And I can't, for instance, calculate X. I can't, for instance, calculate M if I don't already have X. I can't calculate Y if I don't already have M and X. And so it's really to capture and make explicit the fact that this is an asymmetrical relationship, that there's a causal ordering at play. Now, you can make all of this explicit if you sort of expand your DAG to show the sort of computational ordering and all of the unobserved exogenous noise sources, which are sort of implicit in the original graph. we can do that and say like, well, X here, we pass in some exogenous noise UX into a function FX, and that gives us our variable X. And then M here, for instance, we pass in X into a function FM as well as UM, the noise, and then we get M and so on. So you can make this explicit, and it's worth understanding that this is what is implied by your directed acyclic graph. But by and large, we leave all of this out. When you come to generate your own data, which we will be doing in R and Python, it's actually very handy to know about all this sort of underlying implied causal process, because then we can actually make it explicit and generate data according to that process. But generally, we leave them out. Unless these unobserved noise variables are correlated, because if they are correlated, it means that there's actually an unobserved variable that correlates those two variables. So for instance, UM, UY, and UX here are called exogenous. They have no parents. These variables have no parents. But if there is a parent that's sort of shared between these exogenous noise sources, then we might represent it, say, as U here with 2 dashed lines. In fact, it's as you wish. You could call this anything you like, and you can use any sort of arrows you like. Just has to be clear that that's an unobserved variable that's correlating the exogenous, what would otherwise be exogenous noise from M for M and Y, so UM and UY. Now, you can consider these unobserved variables in a similar way to how we treat observed variables. So the rules that I'm going to talk to you about, you can consider these U variables in the same way, but we have to acknowledge that, okay, well, if we need to condition on those variables, a bit like how we conditioned on gender in that drug treatment example, we won't be able to condition on this noise variable if we don't have access to it. But otherwise, the rules are the same. The reasoning about the graph and the causal processes is the same, but we just have to acknowledge that our data set may not contain that value because it's unobserved, that variable, and therefore we might not be able to do certain things with it. In terms of some terminology you might encounter in this structure here, we can say that A is a parent of B, B is a child of A, C is a child of B, and C is a descendant of A, and A is an ancestor of C. So you might encounter that kind of terminology, and that's really what it means. It's all very intuitive. Okay. Now, at this stage, if I was given this talk in person, we might go through an exercise where we consider what the directed acyclic graph of your phenomenon looks like, even at this early stage where I haven't told you the rules and so on and what it really means. But you can start to piece together your directed acyclic graph using, say, in the previous exercise, some of the variables and concepts and constructs that you thought were important to your phenomenon. And so you can start visually piecing together your assumptions about the underlying causal process. And then as we go through the course, you can expand on it, include more variables, include more links, change links, and so on. So as part of that process, I would imagine you sort of come up with a number of difficulties, at least some of you. Firstly, particularly for anyone that's studying real-time processes, but also notice what other challenges that you encountered when you were developing these graphs. In particular, how you would collect the data. So when you start to really represent your theory as a graph, you should sort of do so in a way that's sort of, at least at the moment, agnostic to the way you might later collect the data, because you could also then draw a graph based on the data you've collected so that that graph is consistent with your data collection methodology. But at this point, it should be really most motivated by your theory, not by your data sets. And to that extent, it may strongly influence how you collect your data and whether certain variables can or can't be collected. So for instance, if you have some unobserved variables there and you don't know what they are, you just say, well, these variables are correlated, but I can't explain why, you're going to struggle to collect data for those, and that's going to influence your research methodology. Similarly, for anyone who is studying real-time scenarios, that is phenomena that evolve very rapidly over a matter of milliseconds or seconds, drawing the graph for those processes can become very intractable very quickly. So for instance, if you have two people that are talking to each other, you may have sort of this unfolding causal effect where A causes B, but A also influences A at the next time step, and B is influencing A at the next time step, and so on. And you keep unrolling this, and it becomes incredibly complicated very quickly. And it also becomes difficult to define really what a cause means. When we say that B causes A, what is really meant by that? It's hard to really specify a single path. Are you, for instance, just looking at this path here? Well, what about what came before it? Because if I look at this effect from B to A, I also somehow have to acknowledge the influence of the B at the previous time step on the current version of A. And as we extend this to sort of longitudinal data or just unroll this graph further, we expose ourselves to other unobserved confounders that may be influencing both B and A at the same time that we can't account for. And so you may very quickly find that you can't collect data for this, or maybe it's difficult to define what you're interested in. It defines also how often you need to sample the data. So for instance, if I don't sample B&A often enough, maybe I've missed an interaction that's core to the modeling of this process. Again, we may miss these unobserved confounders or these mediation processes here. And if you really want to model just the fact that this is a bidirectional process where B influences A on unknown timescales, maybe sometimes it's a very quick interaction, maybe it's a very long-term interaction at other times, how do you really model that? And I think here it will become quickly evident as to whether or not you can use the rules of DAGs to achieve what you want. You may have to go down sort of dynamic modeling routes instead, using, say, differential equations, ordinary differential equations, or stochastic differential equation models. But nonetheless, the process can still be useful to highlight the challenges. So even if you find that, okay, well, I've drawn the DAG and I realize I can't collect data for what I need, well, that was still an incredibly valuable result to realize, especially early on in the research process, because then you can consider whether or not you can say, look at some kind of aggregate or some abstracted version of this graph. Maybe you're only interested in what happens at the beginning and the end of this process. So you can sort of represent it maybe similarly to how it's given here, but say, well, at the end of the day, all I'm interested in is some intervention at the beginning of the process and how that results at the end of the process. So if this is, say, the interaction between a patient and a therapist in a session, you may just be interested in two different types of therapy. So even if you acknowledge that there exists an underlying complex real-time process like this, what you're fundamentally interested in can be abstracted. So this can still be a very helpful exercise, even if you don't necessarily use the exact directed acyclic graph that you specify. And note that if we're interested in real-time processes, like we really are interested in these links, then we have to make sure that our model is correct and that our data are sufficient for estimating those links. And if we don't, then we're kind of doomed to ever achieving what we want. And I've seen this before. There are some theories in psychology that relate very much to real-time processes, but the reality of the data collection and the models that are used are not sufficient to really capture those real-time processes. And you're not going to end up with something that's meaningful at the end of it. So it's important to sort of, again, make those three stages, the world, the theory, and the analysis sort of consistent with each other, so that what comes out at the end of this research process is actually meaningful. Okay, so let's start talking about these rules that I've been referring to. We mentioned before this example, which comes from Brady Neal's talk, about the effect of going to sleep with our shoes on and waking up with a morning headache. And let's say that what we're interested in is really the effect that going to bed with our shoes on has on a morning headache, maybe the chances of us waking up with a morning headache. In other words, the probability of why, given that I go to bed with my shoes on, versus what happens if I don't go to bed with our shoes on. And if we just look at the correlations in the data, and we just collect some data for T and data for Y, and we compute the expected value of Y given T equals 1 minus the expected value of Y given T equals 0, we find that that effect is non-zero. This correlation is non-zero. This difference between conditional expectations is non-zero. And we get that result reflected in a linear model if we just compute, say, Y equals beta 0 plus beta T plus epsilon. If we fit this with ordinary least squares, we find that the coefficient on the treatment here, going to bed with your shoes on, is non-zero also. And so if you just go about this in a regular statistical sense, you come to the conclusion that people shouldn't go to bed with their shoes on. Now, obviously, we know that there's a third variable here that explains why people might go to bed with their shoes on and whether or not they're going to wake up with a headache in the morning. And also the fact that we know that there's a zero effect between these two things. And indeed, if you run the analysis conditioning on alcohol consumption, if you run, say, on average, the expected value of Y given T equals 1 and whether or not they went to bed, whether they drank that evening, you find that actually the difference is zero. There is no difference between people that go to bed with their shoes on or not, if you know whether or not they woke up, whether or not they drank alcohol. And so the same thing is reflected here. If we run the model, a linear model conditioning on X as well, we found the beta coefficient on the treatment is now 0. But it's really important to know the causal structure in order to, again, understand whether or not we should condition on alcohol consumption. And indeed, in the previous examples that we had at the beginning of this lecture, we saw that with blood pressure, we shouldn't condition our blood pressure because it was part of the causal process. Here, alcohol consumption is something that explains both whether we go to bed with the shoes on and whether we wake up with morning headache. It's not actually part of a causal process between going to bed with our shoes on and morning headache, and therefore we need to condition on it. And so to this extent, we need to understand both independence and conditional independence. And independence and conditional independence are quantities that describe the statistical relationships between variables as implied by the graph that we suppose. And so we'll talk about this in more detail. And if we're in the linear world, linear land, we can use correlations to measure these statistical dependencies. If we're going nonlinear, we may need other measures of statistical relationships, statistical associations. I'm not going to talk about these other measures of statistical dependence. One example is mutual information, but these are quite difficult to calculate reliably, particularly in the non-parametric case. And so in general, and certainly for this course, we're going to be sticking with the linear associations under the assumption that it does generalize. These rules do generalize beyond linearity, but it's just harder to describe. So what we're trying to do here fundamentally is really to try and acknowledge both sources of correlation and statistical dependence that arise due to causal processes, and also acknowledge statistical dependencies that arise due to non-causal relationships. So I've tried to indicate this here with this sort of thin dashed red line as a non-causal statistical dependence between treatment and outcome. In other words, because there is a common cause of both the treatment selection and the outcome, these two variables are going to be correlated. They're correlated, as indicated here, by virtue of this sort of forked path between C and T and C and Y. But at the same time, there is a statistical association that arises due to the causal relationship between T and Y. Here, treatment causes some mediator, and the mediator causes some recovery. So here we really want, the goal is really to try and isolate these two different sources of statistical dependence, to separate them so that we can extract what we actually care about, which is this causal statistical dependence that arises due to the underlying true causal relationship between T and Y. So we acknowledge, therefore, that there are two paths that exist that result in statistical dependence. One is non-causal. Here, if we can't follow the arrows through C, and the other is causal. We can follow the arrow from T to M to Y. And in order to do this, we can condition on certain things. And if we condition on certain things, we can isolate what we care about. And that's going to be the process of backdoor criterion, which we'll talk about in the next lecture. But in order to understand this, we have to go through the rules of DAGs. Again, we can think about this either in a continuous or a discrete case. But this expectation is really to consider the fact that there are multiple possible outcomes and we're taking an average over them. That's the notation that we're going to be using primarily to describe whether we're conditioning. And actually, it's very simple for us. It makes it very convenient. We can just write the expectation of Y given and then a list of conditioning variables. So I'm going to talk you through three rules now. And in fact, the first two are kind of the same. So you only really have to learn two rules. But once you've got these rules, you'll be able to use DAGs to tell you whether or not you should condition for something. We also use the words adjust for something or control for something. And I hope that it'll shed some light on what a control variable actually should be or is, at least in the ideal case. And I think this might be quite different to what generally gets taught on most statistics courses. So let's start by looking at the chain A to B to C. We see that statistical information flows from A to C through B, and this is indicated with this dashed line here. This is supposed to indicate that a statistical dependency exists. So for instance, A is related to B, so we've got this statistical dependence line through B. B is related to C, so we've carried it on from B to C, and also A is related to C as well. So we have this statistical dependence that exists between all three of these variables. So if we collect data for A and C, they will be correlated or statistically dependent. If we can collect A and C, and we have two columns in our data set, we look at the correlation between them. Indeed, that correlation will be non-zero. And this dependence arises as a result of this particular causal structure. So what we can say at this stage is that the expected value of C given A equals 1 minus the expected value of C given A equals 0 is non-zero. And this again gives us essentially the coefficient in a linear model where C is the outcome and beta A is the coefficient on A that tells us how much A is related to C. And again, we find that that is non-zero. So in this case, if we just have two variables and we run this model here, we find that A is indeed related to C. But what happens if we condition on B? And indeed, if we collect the variables A, B, and C, we might be tempted to include B as a control variable, as a predictor in the model. But if we do this, what we find actually is that the coefficient on A is now 0, and the coefficient on B is non-zero. So in other words, it tells us that B is related to C, but A is not related to C, even though we know that A actually causes C. It's just a little bit further back in the causal chain. And this is because if we know B, then knowing A tells us nothing more on top. Essentially, C varies for one reason. It varies because of what information comes to it from B. And if we already know B, B contains all the possible information about C that's relevant to C that we have access to. And A is just a sort of noisier version of B because it's less proximal. It's less causally close to C. So in other words, when we control for B, we block the statistical flow of information from A and C. We're effectively controlling for a mediator. And it's something that we shouldn't do. If we're interested in the effect of A on C, we shouldn't condition on B because B essentially contains all the information in A that is also in C. And an example of this that I saw in a talk, which I can't remember right now, is can you predict height from biological sex if you control for bone length? So in other words, in that case, say height would be C here, biological sex might be A, but B is bone length, in which case, once you know the bone length, knowing whether someone's male or female tells you nothing more about their height. It's just an unimportant predictor in this model. Essentially, the bone length explains all the variance in C which is necessary, and A is given sort of no chance. It's sort of, there's nothing left for it to explain once B is in the model. So remember that what we said is we wanted consistency between these three things. So in this case, our analysis has to somehow incorporate our theory in order for us to get meaningful beta coefficients out of our linear regression models. And what we're going to see again from different structures is that we're going to use DAGs to determine which variables should and which variables shouldn't be included in our models. And this is why analysis has to correspond with our model, and why our model needs to correspond as closely as possible with the data generating process. So this point should become more and more clear as we go through the examples. And if our theory is correct, even if our theory is correct, our analysis can't be used to answer the intended research question if it doesn't match the theory. And this is why it's so important to have a clear theory represented as a formal graph, because otherwise it's not clear whether our analysis is correct or not. It's not clear as whether our analysis is consistent with that theory. And if our theory is very verbal, it's very descriptive, very kind of vague at the same time and flexible, it doesn't help us specify our analysis. So what we're going to learn at this stage of the course is to assume that we have a correct theory, and we're going to learn how to go from this theory to a correct analysis, an analysis that is consistent. And arguably, I'm going to argue that we can make this flawless because it's rather a sort of mechanistic process. The harder part is going from the real world to our theory, which is a very difficult thing. For the purposes of the demonstrations and the examples, we're going to assume that our theory is completely correct. So when I simulate data, I'm going to sort of pretending to be God. I'm going to pretend that I know the underlying data generating process and that I can generate data according to that, and that I can give you the correct graph. Our sort of goal will then be to check that we can get the correct results because we know the correct results because we've played God using a process. And part of that is going to involve the specification of an estimand, which is something that we really want to estimate. And that's going to help us sort of express it mathematically to be very clear about what it is that we're trying to achieve. Just as a useful tip, in linear models, which we're going to be using for the examples, we can multiply in some causal coefficients along certain paths to get the total effects. So for instance, if you're interested in the effect of A on D via B, you can simply multiply 0.5 and 0.2, just multiply them together. Similarly, if you're interested in the effect of A on D via C, you can multiply 0.3 and 0.5. And if you're interested in the total effect of A on D, you can simply add together the two separate paths. So here, the total effect of A on D is 0.5 times 0.2 plus 0.3 times 0.5, and that'll give you the total effect, which is 0.25. So in other words, each causal path's contributions are multiplied, and then the different paths are summed together. Now, hopefully we're not going to stay forever in linear land, so when we go to machine learning, we'll have to move away from that a little bit. So let's go through an example of this chain again. And to do this, I'm going to generate some data. And actually, this is where I said when you decompose your graph into not only what's explicitly represented, but also what's implicit in terms of the exogenous noise variables, it's going to help us know how to generate data. I'm going to generate data with large sample sizes for now, and I'm going to assume that we don't have to worry about this finite sample variation, because that is always the case. If we don't have enough data, we can't estimate things properly. But here it's really an exercise to make sure that at least in principle, our analysis is correct. So the first thing I'm going to do for this structure here, assuming that it's correct, is set the research question. We're going to say I'm interested in the total effect of A on C. And to generate some data, I'm going to start off by generating all of the exogenous noise, all of just the random independent noise that contributes towards variation in A, B, and C. So we've got UA, UB, and UC. This is in R code, and I'm going to use the R norm function to specify that these samples, 60,000 of them, are just samples taken from a random normal distribution. So we're going to find that A equals UA, because A has no other parents other than its own exogenous noise. I'm going to pretend that that function is the identity function, that there's nothing else going on. I'm going to say that B here is a linear function of A, so 0.5 times A plus its own exogenous noise UB. And then C here is a linear function of B, 0.3 times B plus its own exogenous noise UC. And so that actually is the full data generating process. I'm pretending that I know that. I've created the data. Some psychologist is going to come and collect those data, and then they're going to run a model. And the goal is to make sure that the model that gets run is consistent with this theory and the research question that they're asking. So in other words, to start off, let's say that we're interested in the effect of A on C. Here we can compute the effect of A on C as 0.5 times 0.3, which is 0.15. And we want to check that we can recover the total effect of A on C by running this linear model. So here in R, we can specify that as LM, and then we open the brackets and specify C as the outcome variable. Tilde is equivalent to sort of what we're regressing it onto. And then A plus B specifies we're including both A and B as predictors in the model. So we're going to fit this and then look at the results. And what we find is the coefficient on A is given to be 0.00069, and it's not significant. Now, this is the wrong result. The research question was the effect of A on C, but actually it's given us an effect of A on C of 0. Now, in contrast, note that the effect of B, which we're not interested in here, is 0.31. Now, it's actually true that the effect is 0.3, so that is correct. But A, the thing we care about, is not correct. So here we might come to the incorrect conclusion that A has no relationship to C whatsoever, at least not if we condition on B. Now, in contrast, if we don't condition on B and we just include A here, what we find is that we get an estimate that is correct, 0.15 or 156 here, which is the correct total effect of A on C, 0.5 times 0.3. So here we ran the linear model with all three variables, and here we ran it again without the mediator included. Note that we can also come to the same conclusions if we treat the linear regressor as a black box. Of course, when we ran this analysis in R, it gave us all these coefficients, standard errors, and everything, statistics. Fantastic. But what if we don't have access to that? What if we're using a machine learning algorithm? We can come to the same conclusion if we treat that linear regression as just a black box. We fit the model here, and then we can create two new data sets. This A1 is essentially a copy of the original data set where we set the value of A to be equal to 1 for all values. Then we create another copy, A0, where we set the value of A to be 0. So this code here just sort of combines all the values for C from the original data set with the repeated value 1, and the number of repeated values is the length of A. So it just creates a big long column of 1s and here a big long column of 0s. We create those two new data sets, make sure everything's named correctly, all the variables are named correctly, and then we pass that new data into a predict function. So the predict function takes the model that we trained up here, the original linear regression model, as well as our new data, A1 and A0. We can generate those predictions, and I'm going to call that C-do1 and C-do0 for those two sort of interventional data sets. I can take the difference between those predictions and compute the mean, and it actually gives us the same result as the coefficient that we got in the previous model summary. So this is the alternative approach that we'll be using much more for machine learning. This is actually a sort of plug-in estimation approach where we sort of have two different estimators, C-do1 and C-do0. We plug them into the expression for our estimand, which is the difference between these two things for the average causal effect of A on C. and then we compute the mean. And that gives us the same value as this coefficient here, 0.0156. So our theory, assuming our theory is correct, and again, we played God, we assumed that this was the correct theory. We guaranteed this when we created the data ourselves. And we knew that the effect of A on C was non-zero. In fact, we can compute this because, again, we created these data ourselves. It was 0.15. But whether we included B in the linear regression model dramatically changed the results. In one case, we found A was not related at all to C, and that was incorrect, obviously. And then the other, we got the correct result for C. So in other words, the analysis, if it's consistent with the graph and we know which variables to include, we get the correct result. If it's not, we get the wrong result. And so these rules are going to help us decide when we should and when we should not include certain variables from the analysis. Without this graph, we have no way of doing that. We have no way to really know whether or not the conditioning statement is consistent with the graph. Now, of course, in practice, we probably don't have the correct theory either. So it's worth bearing in mind that even though I can teach you the rules to help you go from a graph to the analysis, we're assuming that the graph is correct at that point. But of course, your graph itself may be misspecified as well. So it's really about reducing the chances that we've made a mistake and we've done the best that we can. I wanted to also demonstrate the difference in terms of this process between R and Python. I didn't need any libraries beyond the sort of base libraries in R for that previous analysis. In Python, it's a much more general language than R. We need to import some statistics libraries. Stats models to API follows a similar sort of process to GLM in R, and NumPy is just sort of a number or array matrix wrangling library that's very common, very useful, and Pandas is just a way to sort of store data frames in the same kind of fashion to how R does. But otherwise, the translation is all quite straightforward. These steps are sort of practically identical, other than this is R norm, this is mp.random.randn, but other these are literally identical, and then we create the data frame and run the analysis. So if you're interested in this, spend some time, make sure you can do the translation. If you're using R rather than Python, have a go coding this up. If you're using Python, have a go coding this up, make sure everything's running nicely for you. At this stage, I'd like just to have a reflection about the fact that what we've discovered, that if either our model disagrees with the world or our analysis is not consistent with the model, then we have a good chance that we're going to get some pretty meaningless analyses. They can be arbitrarily biased. Before in the example with the chain, we had a true value of 0.15, but when we got the model wrong, we got a value of 0. And it can be also flipped the other way around, as we'll see some other examples. It can actually flip the sign of the true effect. And I want you to sort of ask yourselves, how many times do you think this happens in general practice? How often do we either get the theory wrong? And arguably, that's a bit of a loaded question because we don't really have formal theories in psychology. And secondly, how often do we get the analysis wrong? i.e., how often is our analysis inconsistent with the theory? Again, a bit of a loaded question because our theories are not sort of formal enough to make that step in a sort of consistently meaningful way anyway. But just have a think. So this brings us on to the first rule, and we're still going to be considering this chain structure. And what we have to do is actually start listing what are known as the conditional independencies, which are implied by this graph. In other words, the data that are generated according to a data generating process specified by this particular structure comprise or contain within them a set of statistical associations or dependencies. And these are going to be indicated with this symbol here. This symbol means not independent, and that strike through means not independent, and the underlying symbol that's sort of like an upside down T denotes statistical independence. And so the first one here is to note that C is not statistically independent of A. In other words, C is, in the linear case, correlated with A. We can also say that C is not independent of B, and we can say that A is not independent of B. So this really just captures the fact that all of these variables are sort of dependent on one another, so long as we don't condition on anything. So as we don't adjust for anything or look at a subset of the data and so on. Now, the extra conditional independency that's also implied by this graph is what happens when we do actually condition on something. So here, arguably, we're conditioning on the empty set, but here, if we condition on B, we have a different conditional independency. So here, that strike through that was in this not independent is gone, and we see that C is now independent of A. So C is independent of A given B. And actually, as we've just seen, that's what we simulated in R to see what happens to our beta coefficient on A when our outcome is C and we do not condition on B. We see that the coefficient on A changes from 0 when we condition on B to non-zero when we don't condition on B. And so in other words, if our data are generated according to this sort of process, there exists within those data, between the variables in those data, in that data set, a number of sort of correlations that we can estimate from the data. And actually we can sort of predict what those correlations are going to look like beforehand if we know the graph from which those data were generated, or according to which the data were generated. So this is the first rule. In other words, for a chain structure where we have A to B to C, or indeed the other way around, C to B to A, we know that all the variables are sort of statistically associated with each other on a pairwise basis. But when we condition on B, we essentially block the statistical flow of information that exists between A and C. So that's the first rule. And as I said, these are known as independency statements or conditional independency statements. Here, the conditioning set is empty. Here, we're conditioning on B. So this is the first rule, to know that if I condition on the middle variable in a chain, I essentially block the statistical dependence that exists otherwise between A and C, rendering them independent of one another. So rule 2 is actually very similar to rule 1 in the sense that we can still consider this a very similar structure, but we've just sort of changed the direction of one of the arrows such that we have a fork. So here B sort of forking away, splitting to cause A and C. And here again, we have A is statistically related to B, B is statistically related to C, and also A is also related to C. So if A contains, derives from the same causal parent, in this case B, it stands to reason indeed that C would be correlated with A because they both have the same parent. And so here we can also go through that process of writing out the independency or conditional independency statements where we say C is not independent of A, these are correlated with each other. C is not independent of B, also correlated, and A is not independent of B, also correlated. So again, on a pairwise basis, just as we had for rule 1 for the chain, for rule 2 in the fork structure, all these variables are on a pairwise basis correlated with each other. And again, as with rule 1, if we now condition on the middle variable, here B, we render C independent of A. So if we look at the statement here, we see that C is independent of A given B, which is exactly the same as we saw before. And so if you want to translate this into a regression model, you would have C as the outcome, A is the predictor, and B would be the conditioning variable. And here what we would get is a 0 coefficient on A, because C is being rendered independent of A by the virtue of the fact that we've conditioned on B or included B as a predictor in the model. So as an example to motivate this, we can actually look to that example that Brady Neal had that we covered earlier as well, with looking at the relationship between going to bed with your shoes on and waking up with a morning headache. And again, if we play God and imagine that we're going to generate some data and some psychologists are going to come along, collect those data, and we pretend we know the graph off by heart. We assume that we know it and it's true. So a graph is specified as follows. We generate our data such that there is no statistical causal relationship between going to bed with your shoes on a morning headache. So the effect size here is 0. But we also specify that there is a causal relationship between alcohol consumption and bed with the shoes on with a strength of 0.4 and a strength of the causal relationship between alcohol consumption and morning headache of 0.2. So if you look over here at the R code, we generate the exogenous noise and variation implied by this graph. Again, we don't write this explicitly unless these things are correlated with each other. But here we say that these variables are all determined by exogenous noise as well as their parents. So we go through the same process. We specify UAC, UBS, and UMH. We use 60,000 data points again to avoid issues with finite sample variation. We generate these data according to this graph. You can see that AC, alcohol consumption, has no parents besides its own random noise. We assume that there's an identity function between the random noise and the variable, so we just pass the noise straight through. In fact, you don't even need to arguably specify UAC here if nothing happens in this step. Bed with shoes on is now 0.4 multiplied by that AC plus its own random noise UBS. And morning headache is now dependent on also AC up here, 0.2. And you could also include that morning headache is also 0 multiplied by bed with shoes on. But because it's 0, the effect is the same. We don't need to include that link at all in the data generating process. But what we assume is, what we're interested in testing is that there is no relationship between bed and shoes on a morning headache, no causal relationship. So our research question is specified here. What is the effect essentially of going to bed with your shoes on and waking up with a morning headache? So we run 2 models. The first one is we just condition on the main predictor, bed with shoes on. We just run this linear model. And what we find is that there's a small but significant and non-zero coefficient on the bed with shoes on variable. We have a coefficient size of 0.06, which is small, but highly significant. Okay, we've got a very large sample size, so that makes sense. But we also generated these data, so we know that there is, if you do this without conditioning on the proper variables, there will be this sort of biased estimate. And then if we do condition on alcohol consumption, we get the correct result. So now we see that if we run LM with MH as the outcome, morning headache, exactly the same as before, with BS as the main predictor, but now we're including alcohol consumption, we see that we get the correct estimate for going to bed with the shoes on of 0, and it's non-significant here as well. This is the p-value that comes out. So again, just to confirm, rule 1, very similar to rule 2 in terms of how the conditional independencies work. But in this case, we had to include AC to sort of block the sort of non-causal flow of statistical information that flowed between bed with shoes on and morning headache through alcohol consumption. So, you can start to decompose these into sort of separate parts of statistical association. And we'll do that more when we come onto the backdoor criterion. But for now, this is just to demonstrate that you get dramatically different results if your analysis is not sort of consistent with your research question and the graph. And once again, rather than just relying on the sort of free coefficients that we get out of a linear model, you can confirm that you can also create these interventional data sets as well. So I create 2 copies of the data set where I set the value of bed with shoes on to 1. So we column bind the existing outcome, morning headache. Then we create a new variable, which is just the repeated values of 1 with the same length of the rest of the data set. And we create another one where we just create the value 0 for the whole list of the data set. We make sure we name those 2 copies correctly, and then we feed them in separately to the original model that we fit using the predict function. We specify the new data, we store these new predictions, and then we take the difference between these 2 predictions and these 2 interventional data sets, and we calculate the mean. And indeed, we get the same result as the beta coefficient. So brief reflection at this stage. Notice that the rules for the fork, which was this rule we just did, rule 2, and the chain, which was rule 1, were essentially the same. We had 3 variables, but we know that if all the conditional independency statements are the same for both, and if we condition on B, we get the same conditional independencies as well, even though they have very different causal implications, because obviously the chain is actually a mediation structure, A to B to C, whereas the fork, there's no causal path between A to C, even though they're correlated as a result of the causal structure from B. And note that because the conditional independencies are the same, these rules are the same for both graphs. And this also means that the directions of the arrows in mediation models doesn't really mean much. I could reverse the direction of the arrow from C to B to A. Or alternatively, I could sort of swap these variables around. So long as I still have a chain or a fork structure, I end up with the same conditional independency statements. And so if you don't know which way the arrows go in your theory, you can't really just try them out and see which model fits the best. It's really sort of the statistics are the same in all cases. Notice also that the control variables are there to get us unbiased estimation of the thing we care about. We will talk about this more in the backdoor path section, backdoor criterion section. But note that, for instance, in this alcohol consumption case, we included alcohol consumption not because it was our research question, but because it was necessary to give us unbiased estimation of the effect that we care about. And in some cases, the resulting coefficient on alcohol consumption will be meaningless. In this case, it wasn't. In this case, if we ran through it, we saw that when we included alcohol consumption, we got an estimate of alcohol consumption, the effect of alcohol consumption on the outcome of 0.2. And indeed, that is the effect of alcohol consumption on morning headache. But in some cases, it won't be as simple as this. We'll be doing it as part of a much bigger graph, and then it won't necessarily be meaningful to interpret the coefficient on your control variables. Again, those control variables are there to help you estimate the thing that you care about. And so this tends to lead to, when people do interpret their control variables, as something that's generally referred to as a table 2 fallacy, where you have not only a table including the core effects that you care about, but also a huge table with all the control variable coefficients as well, and then detailed interpretations of those coefficients. Really, we should not be interpreting the coefficients on the control variables, right? We need to focus our research question on sort of one particular thing, or you could do multiple things separately, because the way we design our analyses will be oriented around a particular effect. So that brings us on to rule 3, the final rule. It's already there with the rules. And this is the collider rule. So in other words, we have two variables, A and C, that are jointly causal of B. And you can see why here I've got this block sort of notation, where in other words, the relationship between A and C is independent. So I can write these statements: C is independent of A. The relationship between A and C is already blocked by virtue of the structure here. And that makes sense because A and C could independently vary. They may jointly cause B, but there's nothing about A and C in this causal structure that means that they should sort of contain information about one another. They're sort of completely independently varying. And then you have the downstream variable B, which contains information about A and C, which is why here we have C is not independent of B, and A is not independent of B. So obviously these two are correlated, these two are correlated, but A and C are not correlated or not statistically dependent. And again, bear in mind, I'm going to be talking more about linear relationships, so correlations here, but these results generalize to nonlinear, non-parametric. We're sort of talking about statistical independence, statistical dependence in general, not just correlations. And then the other weird thing that happens with a collider is that if you do condition on the middle variable, if you condition on B, all of a sudden we induce dependence between C and A. So now the statement is C is not independent of A given B, which was sort of the reverse situation to what we had with rules 1 and 2. So this is the core thing to remember, is that when you have a collider structure, the path is already blocked. The statistical flow of information already stops at B. But if you condition on B, then you induce statistical dependence between A and C. And I think this is also referred to as explaining away. Bear in mind that also descendants of the collider are also sort of have the same kind of effect. So if you condition on D in this structure, you also render A not independent of not independent of C here, given D. And this is also true of the other situations. If you have descendants of certain variables, or even ascendants in some cases, you have to be careful that these rules don't also apply to those sort of proximal causes, because if a variable is very similar to another variable in this model and it contains essentially the same information, then the consequences of conditioning on that may be the same as if, or very similar, maybe not as strong, but similar to the effect of conditioning on the variable itself. So beware of sort of ancestors and descendants in that sense. Really just think about the fact that there's a flow of information that exists. This D here contains all of some of the information that A and C sort of impart upon it. So if I condition on D, we're kind of conditioning on a slightly noisier version of B. So you can kind of work it out according to sort of shared variance. As a bit of a silly example to demonstrate rule 3 in action, this is also taken, I believe, from Brady Neal's course, but I might be misremembering it. There's a common example that gets used for colliders, which is looking at the relationship between having good looks, being attractive, having acting talent, and being successful in Hollywood. Now, this is, again, a very simplified example, just like the others. But the idea here is that there's no relationship between good looking and being sort of having innate acting talent. These things are independent. You either sort of are born with good looks or you're born with acting talent, or both, but it's random. And there's no sort of causal relationship between them. But in contrast, being good looking does influence your chances of success in Hollywood. And so does being a good actor also influences your chance of success. And so let's say that our research question is really to look at the relationship between good looks and acting talent. We know that there's no causal relationship between them, so we set that to 0. We play God, we generate data assuming that this is the true causal graph. And then we see if knowing that graph helps us get to the right result. So we're going to generate data in exactly the same way as before. Arguably, some of these are maybe binary variables, not normally distributed variables, but in that case, feel free to swap these out for, say, R binom, which is the function in R that allows you to generate zeros and ones. But otherwise, we're just going to keep it simple, keep all these Gaussian for now, and then we're going to generate the data. So you can see that good looks has no parent, so it's just sort of its own random noise. passing the identity, using the identity function to pass through the Gaussian noise we generated. Same with acting talent here. It's got no parents. Arguably, you could include plus 0 times good looks if you wanted to, but the effect is the same. There's 0 relationship here. And then success in Hollywood is sort of a jointly caused by 0.4 times good looks and 0.3 times acting talent plus its own random noise USH. So that's how we generate the data. Now we're going to run some models. And the first thing that you might do is just include, for instance, acting talent and good looks. So the outcome variable is acting skill or acting talent, and the predictor is good looks. And if you run this model, you actually get the correct result, that the effect of good looks on acting talent is 0. It's non-significant. Fantastic. But it's quite common in research to include more control variables rather than less. So if you want to err on the safe side, the general sort of philosophy seems to be that, we should include more variables just to make sure we're controlling for everything we should be. But in this case, it will give you the wrong result. So if we do condition on success in Hollywood, we actually induce a negative correlation between good looks and acting talent. And actually, this tends to be the case. If you have two colliders that two variables which jointly cause a collider, and these relationships are positive, conditioning on the collider will induce a negative relationship between them. And it's kind of like explaining it away. If you're good looking and you're successful in Hollywood, you're less likely to also be a good actor. Or if you're a good actor and you're successful in Hollywood, you're less likely to also be good looking. So it's really about the sort of confluence of multiple things at the same time. You're less likely to be both of these things. So you induce this negative correlation between them. And so you can see that when we do condition on the collider, we get the wrong result in this case, assuming our research question is looking at good looks on acting talent. So again, as we'll talk more about in the backdoor criterion section, there's sort of like a flow of information between good looks and success in Hollywood, but then that is sort of blocked according to rule 3, unless we condition on success in Hollywood, and then it opens up a path, and then we get a sort of spurious path linking good looks and acting talent where there actually is none. So they're the 3 rules. Rule 1 for the chain, rule 2 for the fork, and rule 3 for the collider. And with these rules, we're going to see how we can use them to really extract or estimate causal quantities from observational data. So sort of really to go from correlation to causation. The reflection here is really to be clear that we really need to consider what the structure is in order to know whether to control for the variables. And here's the summary of the key relationships. In rule 1, we have a chain structure. C is independent of A given B. So if we condition on B, we block that path. For the fork, C is independent of A, also given B. So in this structure, if we condition on B, we also block that path. And then finally, the collider, if we condition on B, the path that was already sort of blocked is now unblocked. So we induce correlation between A and C. So C is no longer independent of A given B. Also consider the descendants. In all these cases, descendants may play a role. So just be careful with them. Now, one question that I sometimes get is, wouldn't all this be easier just using structural equation modeling? There's a handy package in R called Lavaan. Also, you may be using M+. There are various packages that enable you to specify a structure, a set of structural equations, and then solve in order to compute the path coefficients, even when you have unobserved variables as well. And the first thing I would say is okay, this is true, you can do this, but it assumes linearity, first of all. And also there are other reasons not to do it, which I'll come on to. But let's just pretend we do want to use SEM. Let's say we have this graph here. How would we go about using SEM? And you can do it. It is a solution to this problem. We can generate data according to this structure here. I'm not going to go through that. Just trust me, this is how the data are generated. We create a data frame. And then with the package Lavaan, you can actually specify the structure here, sort of one outcome or one variable at a time. So for instance, we see that D is a function of B and C. So we simply write D tilde B plus C. It tells us that D is an outcome of both this path from B and this path from C. We see that B is dependent on A. So we have this B tilde A here. And then we have C here is tilde A, which tells us that C is a sort of child of A. And so with this model specification, you can actually compute altogether all of these paths at the same time using, for example, the SEM function here. So we have S is the model equals SEM mod, and then feed the data in. And then we look at the summary. And what we find is that indeed it gives us all the correct results. It gives us results for each of these paths. B to D is 0.2, C to D is 0.5, A to B is 0.5, and A to C is 0.3. So that was all correct. So if you are confident in the structure, you can use SEM to estimate all those paths. And people that are already using SEM may, at least some of them, in fact, most of the time are reluctant to admit that it's a causal modeling framework, and it is. You're explicitly specifying the causal structure behind the data here. And it's a shame in a way that it sort of gets obfuscated by the desire to sort of hide the fact that this is a causal model. But nonetheless, people are already using this, which arguably is a good thing. But the trouble is, we don't really want to spend forever in linear land. We don't want to assume everything's linear all the time. Also, we may not need to estimate every single path in this model. So even though we may need to specify these paths, say, in order to estimate a particular path, so we're interested in the effect of A on D, we may also want to include this route here. But nonetheless, it's sort of a bit of a waste, because we may actually only be interested in one particular path. But with the SEM model, you end up computing all the paths that you specify as part of that model. And it also means you may not ever learn the rules, which can give you a lot of advantages in terms of generalizing to nonlinear situations, and also being able to optimize your analysis for a particular estimand. And that may mean that you don't need a lot of variables in your graph. We'll talk a little bit more about that in later sections. So as a summary for now, directed acyclic graphs, we need a graph in order to know which variables to control for and which to not control for. This leads to a set of good control variables, i.e. variables that we should condition on, and bad controls, variables that we shouldn't condition on. And in order to decide that, we need the context of the whole graph. We need the research question. And so we'll give some more examples of that later on. And if we don't get this right, the coefficient estimates will be arbitrarily wrong. We've already seen that in certain situations with certain structures, if we include a control variable, we may reverse a sign, we may bias a sign arbitrarily. And so we can get some very meaningful results or some very meaningless results. So we really need to know which variables to control for. Furthermore, we shouldn't be interpreting the control variable coefficients. They're there to facilitate the estimation of a different thing, a different quantity. So it might be tempting, but in all cases, will it be valid? And sometimes identifying the right control variables is quite tricky, and it really depends on the correctness of the graph as well. We'll talk more about that again in later sections. Really, this section was to help you know these rules, learn these rules, these 3 rules. And if you want to sort of read ahead for next section, consider reading this excellent paper by Cinelli, Forney, and Pearl, called A Crash Course in Good and Bad Controls. That's it for this lecture, and I'll look forward to talking about the backdoor criterion and causal identification in the next session.